So I'm going a bit slow on this homogeneous, heterogeneous, and these concepts of catalysis. If all is trivial, you start yawning. Huh? So then I know I can proceed a bit faster. But I think it's very important that we understand all the basics and the concepts behind, because unfortunately they're not very trivial. And even when you read the literature, you find out that there's a good few. Oh, thank you. There's a good few reports, actually many reports that neglect. You know, they will put down, we added at the beginning mercury, and the mercury drop experiment didn't show. But then they don't explain why, what they do, when they add what, how much, and then the whole thing, the whole description becomes actually useless. And in the end, it's not about having a homogeneous or a heterogeneous catalyst, but knowing whether it is homogeneous or heterogeneous. And sometimes you have, when you start designing your research project, you have an idea, you'd say, I make a homogeneous catalyst, and then you find out that it isn't, and this is painful, because you had, your model in your head was already there. But I think the key of us as scientists is not to show that our model, that everything we do fits our model, but to explore which models describe the system properly, and how do we have to expand the model. So I try to tell my students that actually the best thing that can happen is something that doesn't fit the model, because then we have to expand our model, and that's progress. We have a better understanding. So if everything just goes the way everybody says, this is, in the end, okay, it's nice, but it's boring, because there's no expansion of knowledge. So I think in the end, it's much nicer if we have things that are beyond the model. So that's why I put a bit of time on these concept things. Huh? So we discussed, now I will fall sooner or later, but don't laugh. So we discussed the visual test, the poisoning, that we have to be careful how we poison, the kinetics, important, but as I said, not unambiguous, because the sigmoidal curve can be because of catalyst activation, and catalyst activation may be an excuse for actually something that's sigmoidal. I think the emphasis here is the variability in the heterogeneous system and the reproducibility in the homogeneous system. So if this is a programmed activation, we always see a bit the same. And we just have now an iron carbene system that requires this. We don't understand why and what happens in the activation, but the activation is as well substrate dependent, and with one substrate it takes 5 minutes, and then the reaction goes, and it goes like a pistol, like a rocket. Within 2 minutes everything is done, but it takes 5 minutes to get activated. We take a less active substrate, it takes 20 minutes to get activated, but it's not once 30, once 10, once 15. No, it's between 20 and 22 minutes. So clearly there's a programmed thing. So you could say, okay, if so long induction times, that's that may be a sign for a heterogeneous system. But the fact that the induction time is so reproducible, and if it's decomposition, often it's a minor thing that is actually out of our control. Too much humidity, or a temperature burst at the spot or so, that makes the reaction go. So then there's another test that has been quite prominent is the so-called three-phase test, where you put either the substrate, you immobilize either the substrate on a support, or you immobilize the catalyst on a support, or you immobilize both on a support. So if the support is decomposing to provide the catalytic active species, you'd see that in one case the system cannot make an encounter, and in the other cases you can. So imagine you immobilize the catalyst, but the catalyst decomposes. Then the immobilization is not static, so the substrate can reach the catalyst. If the substrate is immobilized, the catalyst has to be homogeneous that the substrate gets immobilized, gets converted. Now you may see that there's a bit of a penalty in this quite rigid system, because if you have to immobilize once your catalyst, once your substrate, this is a major synthetic effort. So you take a Merrifield resin or so, and you start immobilizing your ketone or your olefin. So already your olefin changes reactivity because it's not the same anymore. Your ligand, you have to decide which ligand you want to immobilize. So it's a fairly rigorous test, but it's not done in a few hours, not in a few days. It probably costs you months to do that three-phase test. So that's a bit of a, but once you have the process installed, you can screen a whole set of catalysts. Then another indicator is typically the dependence of your reaction rates on the catalyst loading. So if you have a homogeneous catalyst, typically the catalyst is has a first order rate dependence. Now I have to open a parenthesis that depends on the mechanism. Sometimes two metals have to interact, so it becomes second order, or there may be a different dependence in different steps, so it may get a broken order even. So that the dimer is the resting state and then it has to go back to the active state. If this is the rate limiting step, you get a broken reaction order. But independent, you should see a fairly clear dependence of the catalyst loading on the reaction rate in homogeneous systems. If you heterogenize your catalyst, this is different. Because in heterogeneous systems, as I tried to draw you very schematically, the structure, the surface plays a role. So especially when you form nanoparticles, there's only so much, there's an optimum size of the nanoparticle. Too large particles will have very low activity because only a small portion of the metal is at the surface and can be catalytically active. So small catalysts are actually very hot, very active. So you may find with heterogeneous systems, if you start from a homogeneous complex, the smaller the loading is, the higher the activity is, which is counterintuitive for a homogeneous thing, but for a heterogeneous it may just be that you stabilize your nanoparticles better, they stay smaller, small particles, higher relative surface area, better catalysis. Filtration experiments may be very good. So you filter in the middle of the reaction, you do a filtration, you have to have nanofiltration membranes or something of that kind. You filter. If the reaction continues, you likely have a homogeneously dissolved active species. If your conversion stalls, means that you filtered off your catalyst, your substrate, your product got filtered through, but now there's no active species. Can have its pitfalls. I'll show you an example in a second. Then we can of course do physical measurements. We can use dynamic light scattering, transmission electron microscopy to see whether we have particles in our otherwise clear solution. And these particles would then indicate that there may be a heterogeneous layer. Now what these measurements won't tell you is A, whether that heterogeneous layer is the catalytically active species, and B, very small particles won't be measurable. So light scattering goes maybe to 2 nanometer diameter. And that's just where the hot area appears. So palladium nanoparticles for cross-coupling, they're often in the 1 to 3 nanometer dimension. So many of them will escape light scattering proof. Then another, maybe I can group this together, chirality, selectivity can be a very compelling case for a homogeneous catalyst. Because if we can change the selectivity, the chiral induction by our ligand system, that tells us that probably the ligand plays a role. So if the ligand plays a role, probably it's a homogeneous system. So chirality transfer from the ligand to the product is often a good indicator that we have a homogeneous reaction mixture. Now, maybe the caveat that I have to open here is that not seeing a transfer is not an indicator for heterogeneous catalysis. So this is only in the event that you have a very useful chiral pocket, you see chirality transfer. But many catalysts are totally chiral, but the chiral pocket is so unselective that your EE in the reaction is still around 0. So it could be totally homogeneous or could be heterogeneous, and unfortunately most of the chiral ligands give very low EE, and only a few make it to JAKs and give you 90+%. Lucky you if you have it, we never had it. So you see that there's, in all those experiments, there's always a but. And to mitigate that but a bit, we need a combination of experiments. So we need to do 3, 4 orthogonal experiments to make sure, that's what we see. Let me give you an example that we looked at in a case study some years ago, where we synthesized 2 types of palladium complexes. And those of you involved in the carbene chemistry, they see that this is a normal and this is an abnormal carbene. They have slightly different donor properties. Well, no, actually not slightly. They have quite distinct donor properties. This ligand is a much stronger donor than this one here. So the palladium becomes electron richer in that case. And we thought, well, we could show this by a variety of techniques. We could show that this palladium is actually nucleophilic, while this is classically electrophilic. Now, palladium-2 is generally electrophilic. That's why we can do allylic substitutions. That's why we can do cross-coupling, because the palladium-2 is electrophilic enough to get reduced to palladium-0 to enter the cycle. So we were wondering, what can we do with a nucleophilic palladium? So something that likes to share its electron density. So typically this would be bound for oxidative addition chemistry if something is electron rich. So we thought we can do bond activation, we can activate dihydrogen, get oxidative additions, make a palladium-4 compound, which can then share its dihydrogen and start to reduce olefins. And indeed, this works quite well. We used a dummy substrate, a simple one, that has no selectivity issues, no cis-trans effects, no nothing. So it's the easiest to use. And you'd see that the red, the abnormal carbene, is constantly significantly outperforming the normal one. So this all fits. We were happy. There's a clear trend that electron-richer palladium is oxidative addition, and so we have higher activity. And we see as well there's a trend in solubility or in solvent dependence, and at the beginning we didn't stand still too much. But then some of you may be familiar with transfer hydrogenation, and if you're not so much, we'll talk much more about it tomorrow. These solvents are more than just polar solvents. They can formally as well donate dihydrogen. So they have a reducing character, those systems. And what really struck us was then that when we started looking at this reaction a bit closer, the PhD student at the beginning got nearly mad. Because once the reaction in ethanol was finished in 2 hours, and once after 3 hours she had 10% conversion, but after 3.5 hours she had full conversion. And once she had 6 hours, nothing, and she was about to throw it away, and to the 8-hour sample, sure, everything got converted. So there was this strange thing of that system, it boiled off at a random time. Mercury was inhibitive, and the kinetics, once we followed it narrowly enough, we saw that sigmoidal profile. So these 3 points together, they formed like a cocktail of likely there's a heterogenization. So we thought, okay, can we nail this? And we did a set of experiments where we combined two analytical techniques together, where we used light scattering, where we monitored the reaction, are there particles formed, and in parallel we looked at the conversion by GC, gas chromatography. And you'd see in this left plot, you see a classic reaction profile. So the blue pillars refer to the hydrodynamic radius on the left scale, on the left x-axis, and the dark blue dots relate to the conversion on the right side of the axis. And what you'd see is that there's a consistent buildup of layer battery. Well, doesn't matter. Let's keep it. So you see there's, as the conversion increases, there's as well a buildup of particles, which makes sense in the context of the previous experiments, but it doesn't tell us that these are the catalytic active species. So what we did is we filtered at different intervals. After 2 hours we filtered, and as a consequence you'd see after 2.5 hours there are no particles. But we didn't filter everything off, because in the solution there was still palladium complex, and after 4 hours, after another 2.5 hours, we see particles being formed again. And as the particles grew, conversion grew. And you see this perhaps more strikingly here, where we filtered after 4 hours. You see at the beginning we filter, after 2 hours we have some conversion and some particles, but not too large particles. Then we filter after 4 hours. After 4.5 hours, we don't see any particles. We left it steering. As the particles are small, the conversion didn't progress. But clearly we didn't filter the homogeneous part, because there's still palladium in the solution, and as we left it for longer, the particles grew, and sure enough, the conversion raised again. So this set of, like here we have now 4 or 5 different parameters that we can combine, and they're all consistently telling us that the phase is heterogeneous. So we could come up with a mechanism that is still dependent on the high electron density at the palladium. So we think there's some olefin coordination, replacement of the nitriles. Then we get oxidative addition. And here we don't get reductive elimination of migratory insertion first, but we get reductive elimination of the hydride and the carbene. So we form this imidazolium salt. Or we can do this twice, and then we get a palladium tetrahydride or a tetrahydride palladate, which is not stable. We all know this reductively eliminates, giving palladium 0 and dihydrogen. And the palladium 0, of course, if it's small enough, it's a superb hydrogenation catalyst. So we make here palladium on carbon without much carbon, but very hot palladium. So we think then the palladium aggregates, and that's the active species. Or maybe some palladium expels and gets it. And here now we generate in the same time an imidazolium salt, and ammonium salts are known to stabilize palladium nanoparticles. So this all makes sense that once we have the particle, it's very active because it stays small, the imidazolium salt stays there. And we have some evidence as well for such reductive elimination. If we use chlorine instead of dihydrogen, we get actually the tetrachloropalladate and the same type of precursor, but then it's a carbon-carbon bond formation or a carbon chloride reductive elimination. So here we start with a fully homogeneous system. The reaction stays clear till the end of the reaction. Once we've consumed all olefin, we get blackening. The blackening is clearly degradation. But so here the catalyst activation is not a single step, not just a ligand displacement, but it's a series of events with reductive eliminations, with hydrogen elimination again, with palladium 0 formation. So this is a long chain that gives us the active species. And it's this part here that's here now rate limiting. Once we are in the active species, it goes. Within a few minutes, all the catalysis is done. and once there's no substrate anymore, we decompose the catalyst, we get palladium black. So that's a example how something that is likely homogeneous, you know, you look a bit closer, you realize nothing is homogeneous in the reaction at all. So,
What is the solvent?
what is the solvent? Ethanol here. So, and ethanol is of course as well a dihydrogen source, so it can give acetaldehyde. So the palladium can undergo a dehydrogenation of ethanol, and that helps to accelerate the palladium hydride formation. Yes, yes. Palladium nanoparticles are soluble, yes, but they have to be stabilized. So palladium nanoparticles that don't have a stabilizer, they aggregate, and then you get the palladium black. But most nanoparticles they contain either carboxylates or phosphonates or ammonium salts that stabilize the particle. So if you have plenty of those around, your particle is more stable than if you don't have any stabilizer. Then the palladium surface will meet another palladium surface, you get rapid Ostwald ripening, and the particle grows till it sediments as palladium. That's what we then call palladium black. We run this reaction and we monitor the reaction. We follow it by GC. So we look at the conversion. How much octene, how much octane, or cyclooctane do we have? And we see this is the profile. The beginning very slow, and then after 4 hours we are at 30%, 50%, 100% after 20 hours. Yeah? And we monitor in parallel, we do this in a cuvette that we can put into a light scattering device. You know what light scattering is? So we... Okay, so light scattering is basically you put a laser light through a solution and you measure which light gets scattered. And depending, so if particles are in solution, the scattering coefficient is different, and the difference of the coefficients allows you to tell you how fast the particles are moving. And the faster they're moving, the smaller they are. So you can measure from the scattering pattern that is diffracted, you can measure how large the particles are that you have in solution. You measure the hydrodynamic radius, which is basically a soft diameter. Well, it's half of the diameter, but it's soft. So with light scattering, you get the dynamics of the particle. With microscopy, you boil it down and you get the hard core. So you measure almost the same, but the sizes change. So with this light scattering, we can basically see what type of particles we have in solution. Now, because the scattering intensity increases rapidly if you have with larger particles, with light scattering you only see the largest particle. You don't see the small ones. So if you have 10 nanometer particles and 100 nanometer sized particles, light scattering will only show you the big ones, because they have the biggest scatter. So those are visible. So with the light scattering, we can look at the same solution. With GC, we determine how the catalysis, the catalytic reaction is progressing. With light scattering, we look what the solution contains. Does the solution contain particles? Yeah. And then what we did is at different times, we took the whole solution, filtered it through a nanofiltration membrane into a new cuvette. So everything that was a 250 nanometer cutoff cuvette, nanofiltration membrane that we used. So all the large particles stay in the membrane. So when you just look at the pillars, you see after 2 hours, when we filter here after 2 hours, then obviously we just removed all the particles. So the solution is not only clear by eye, but it's as well by light scattering. There's no particles 20 minutes after, 30 minutes after filtration. But we only filtered the particles, and some of the palladium complex aggregated to nanoparticles. Some of the palladium complexes were still in their pristine state, in the pre-activation as complexes. So those we didn't filter. Those went through the membrane, but as the reaction progressed, they started aggregating. And that happens even after 4 hours, or after 1 hour. This is the same. After 4 hours, it's the same. The particles, not all palladium got aggregated into particles. So some palladium went through here, but some stayed here. And so you see that there's no particles after filtration after 4 hours. Here there's no particles after 2 hours, but after 4 there is. And then what we see is that if there are no particles, that's it. If there's no particles, we don't get any conversion. And only once we get particles formed again, the conversion rises. Does that make sense? You ask, or you yawn. This holds, and I don't take it as an insult, or not as a huge insult. So, mechanisms very tricky to elucidate really. Maybe with trapping, with such type of experiments, we're able to get a bit of an idea. Spectroscopy, monitoring a reaction by spectroscopy, will likely not tell us much, because whatever we see by spectroscopy is some accumulation. So if you think of a catalytic reaction or of an energy profile, can you see this? And I'm right here. So if I look at the catalyst, it gets somehow activated, it grabs the substrate, so that's the catalyst substrate, and then it does, oh, thank you. Whatever type of reaction, and we have here, maybe this is the highest activation energy, maybe this one here is the highest activation energy, so that's maybe the rate determining step. But in addition to this, I have everywhere a reversible parking. That, you know, the catalyst can also go to so that's an off cycle. And it may accumulate here, because that's now, apart from this one here, this is the biggest barrier that the catalyst has to overcome. But that's not even a resting state on the catalytic cycle. That's kind of a dormant species that can go back to here and then do the final conversion. And so if we see something spectroscopically, it's likely somewhere here.
Why intermediate is off cycle intermediate?
Because it's not, because from here, unfortunately I can't draw in 3 dimensions, but you have to imagine this coming perhaps out of the table. So it has no direct entry back onto a intermediate, only it has to go back to this one. So it's, okay, so this is the catalytic cycle from the viewpoint of the catalyst on a string as an energy profile. If I draw the same thing in a cycle, then I have here the catalyst, I have the catalyst substrate, I have somewhere here the catalytic intermediate, And here the catalyst product, maybe I should perhaps have drawn this slightly differently. So then this is the product that then after product release goes back to the catalyst. So this is the same, it's the same energy profile, but now cyclic, and now I have lost the height. So I could say, look, okay, wherever it's a bit thicker, the energy is a bit higher. But that's then getting a bit noisy. So the orange one that I've drawn here, that's like somewhere here. Is an intermediate that is stable enough to be formed, to be detected, but it cannot go back to an advanced point of the cycle, but it has to go back. So this has to be totally reversible. So it's not on the cycle. It's off the cycle, and it has to get all back onto the cycle to continue conversion. Yeah? So that's why it's an off-cycle intermediate. And even worse, but I have to state this, sometimes you get even X-ray of so-called catalytic intermediates. Now, an X-ray, you have to imagine what it needs to grow crystals. Now, many of you have grown crystals. You know how dead stable the compound must be so that you crystallize it. So, if you can crystallize a thing, likely the crystal is somewhere. That's not even off cycle. That's off the cycle or that's not an intermediate, that's just off the cycle. This is such a large gap, it will never ever go back to the catalytic reaction. Or it has a huge barrier to overcome. So sometimes you find crystals that are interesting, you redissolve them, you get actually catalytic activity, so hooray, it's a catalytic species. No, it's not, it's just a different type of activation you need. You know, it could be this one here that gets crystallized, and maybe it's not that low, but it's just stable enough. But there's never ever a crystal on the cycle, because for a crystal to grow, it needs to be a thermodynamic sink. A thermodynamic sink means there's no turnover, or very slow turnover. So be extremely careful if you have structural identity of something. It is something that may be related to give you information of what has to happen with the complex during the catalytic cycle, but it's not on the cycle. But you know, sometimes you see the substrate being partially converted, so you know, that's a thing that has to happen in the course. Because after all, it gives you some idea of how you get from here to here. So it's still very useful data, but try to avoid to call it a catalytic intermediate. So that's, do you have any questions for this very generic catalysis thing? I'd like then, so today is perhaps a bit drier, but it's as well a bit shorter because morning we slept through half of the 2 hours for whatever reason. So we would do some more as well exercises then as we go through the different topics. Now, if you do have any questions on the general aspects, that may be a good moment. Otherwise, we maybe move to the next topic. Now, this I don't know. This may be a classic in homogeneous catalysis that you have all been taught backwards and forwards. Then I'm happy to skip it. So who knows about hydrogenation? The mechanisms and the catalysts. Who has done hydrogenations in the lab? Who has not done hydrogenations in the lab? See, that's no difference. That's funny. I used to ask this in, well, no, I have 2 more questions for you guys. Because, you know, in Switzerland is a very democratic nation, at least that's what they say. And democracy means that you vote. You vote about everything. And about many things you don't understand, you're still asked and you have to vote. So I leave it to you whether you've been asked to a thing that you don't understand or not. But so when I did this in Dublin, so my next question was, who doesn't know whether they did hydrogenations or not? Now people are generally silenced, but now I have a fairly thing, you know, I have 3 that did hydrogenation, I have 4 that never did hydrogenations, I have nobody that doesn't know, and I have 35 people here, so, you know, there's the other 29, they're either asleep, they don't give a I didn't say the word, I didn't. Or they're doing texts or whatever. Anyway, so now I think I can rush a bit through it. Again, you have to guide me. So I think my understanding is that we have here 4 days where we can try to profit as much as we can. So you're here, I'm here. We can make a good time out of this and have as much as we can talking and going through. But for this, I need your, you know, I need your activity. So you tell me, Martin, we know this. Okay, move on. Then we have more interesting or we have more specific things. You tell me. Yeah. And the worst is that I tell you here 4 hours things that you've learned 3 years ago. You think, wow, why did that guy travel all the distance? And I look at you and I say, why did I travel all this distance? And why are you sitting here? So then we'd rather go and have a beer somewhere. Okay. I put this as a start, maybe to pinpoint a few of the mechanistic parts down that we can possibly use then as well for the more challenging CH bond activations. And the advantage of dihydrogen activation is that it's a fairly simple molecule, so it's fairly well understood. And that's, you know, physical chemistry makes lots of use of this because dihydrogen is the simplest molecule, 2 electrons, 2 protons, so you can describe it fairly well. So what can you do? So hydrogenations, I would box this in as hydrogenation that is using dihydrogen as the hydrogen source. That's what I would call direct hydrogenation, my God. Some of you have autoclaves, have used this already a number of times. There's a few interesting aspects in running hydrogenations. So one is that alcohols are typically good solvents, and again there may be a double focus and people may not look too much into this because every alcohol is per se a hydrogen source as well. So there may be not only direct hydrogenation but as well other hydrogenations. A very interesting concept that has been developed in dihydrogenation is the so-called biphasic hydrogenation, where you use 2 different phases, and that contributed a bit to the issue of homogeneous versus heterogeneous catalysis and how can you separate products from catalysts from product streams. So some solvents are not miscible and you use them daily when you do extractions. Some solvents have a funny behavior because they're miscible under certain conditions but not under others. So supercritical CO2 is one of these magic solvents for this purpose. Another one are perfluorinated solvents that if you use an organic phase, a specific organic phase, and well, not all perfluorinated solvents behave like that, but specific solvents, they're immiscible at room temperature. You heat this to 60-80 degrees and you get a homogeneous phase. You cool it down, you get a spontaneous separation of the layers again. And this is very attractive because now you can decorate your catalyst with perfluorinated chains. So like a phosphine, like this one here, a phosphine that has these Teflon tails. So it's like a alkane but polyfluorinated. This phosphine has a very high partition coefficient in fluorinated solvents, very low in organic solvents. So you add a rhodium catalyst, You add the phosphine binds to the rhodium and drags the rhodium into the fluorinated phase. Your olefin substrate is an organic substrate, so it stays in the organic phase. You have the substrate and the catalyst, they don't see each other, no reaction. You stir, you heat, the phases become homogeneous. Now the catalyst sees the substrate, conversion can take place. Now you have a homogeneous phase, you let it cool down. Your hydrogenated alkane is staying in the organic phase. Your perfluorinated rhodium complex goes back to the fluorinated phase. You simply extract, add a new organic phase with your substrate, and you can recycle and recycle and recycle. Works very well. It's very attractive from an academic point of view. From an industrial point of view, the drawback is that A, perfluorinated solvents are very expensive, and B, you don't have massive amounts. And if you see in what bulk quantity hydrogenations are done, you realize for a separation this is a huge cost factor. So it's basically, it's like you can do basically an extraction like when you do an aqueous organic extraction. You remove the fluorinated phase back into the reaction vessel, and your organic phase contains the product. And what is back in your reaction vessel can be used for the next reaction. Leaching has been shown to be an issue, and then the other thing that is unfortunately very academic and not very industrial is that extractions, we use it daily. It's our classic, when we do ligand synthesis, extractions are very common. Industry, no. Industry's preferred purification is crystallization in the flask. Basically, you then just decantate off all the solvent, you have the crystalline product, that's what you want.
So you can't get that from purity that you get crystallization?
You may get the same purity, but technically, extractions, liquid-liquid extractions, are difficult on an industrial scale. You have to imagine these reactions in an industrial scale, they happening in 1,000, a 10,000, 100,000 liter vessel. That's nobody is shaking that, But even then you have no tap to move this away.
And so where does CO2 comes in this CO2 magic system?
The acoustics is not very good. You're saying?
So where does CO2 comes into this biphasic catalysis?
The CO2 is, if you pressurize it, CO2 becomes miscible, supercritical CO2 becomes miscible with organic solvents, and then you can do, but it's superpolar. So you have this change, and if you heat it up, the CO2 just evaporates, so you have this way. The other interesting modification is to have these sulfonate phosphines, because they make the compound water soluble. And you'd see, and I'm perhaps losing here a bit my plot, but you see lots of approaches to make catalysis, to perform catalysis in water. People call it the green solvent, because water is water, water is clean, water is abundant, water is a fantastic solvent. I know there have been even books written about how green water is and how much this is a way to go. I think there are 2-3 things that need to be taken into consideration. One is water is only a green solvent when it's pure. And I don't have to come here to tell you how precious water is. So I find it I find it quite unethical to take pure water, put a catalyst, a substrate, auxiliaries in that water, and then that pure water is basically wasted. We cannot do anything with that water anywhere. And purification of contaminated water is a hell of a job. It's very difficult. So I think it's not actually a green solvent, it's actually the worst solvent we can use. Water will be scarce and scarcer, so if we pollute water on purpose, that's idiot. We can pollute any other solvent, we can clean this. Methanol, we can just boil it off, we can distill it. Water, we cannot distill. It's a mess. The other thing is, of course, it's not practical. How many substrates can you dissolve in water? all our pharmaceuticals, all our agrochemicals, they're all organic systems. They don't go in water. So then you need phase transfer catalysts and shidi-bidi, and you lose it all. So it's not convenient. And this is actually quite nicely shown with these persulfonate phosphines. They've been used for olefin hydrogenations. Very successfully by Ron Poulin, they made a whole process. They built a plant for aqueous hydrogenations. But they can use it for one substrate. They can use it for propene. Everything that's larger than propene doesn't dissolve in water, butene, pentene, so you cannot use it anymore. So this is a single substrate process, not very feasible. And you can imagine as soon as you start building up complexity, water is not the best solvent. And you'd see many Suzuki-Miura couplings in water, and people say, oh, we do a green job. I think it's not green at all. And many of those catalytic runs are actually biphasic, so it's messy. If you have a biphasic solution or a suspension, you cannot run kinetics. You cannot run spectroscopy. You cannot run anything because you have always these solvent mixtures. So my advice is stay out of water, or if you stay in water, go for swimming, but not for doing catalysis. So, back to hydrogenations. There's a few things, a few mechanisms we should keep in mind, and I think they're propagating throughout other activations. There's the classic hydrogenation activity, mechanistically, where we have where we start with a electron-rich. That's a bloody stick. I don't use it. Where we start with an electron-rich metal center. We get oxidative addition, or where we get hydrogen bonding and then oxidative addition. We need two properties of the metal center to do this work. One is that we need a free coordination site that hydrogen can bind side on. So this is a sigma complex. It's actually the bonding sigma orbital that is bonding to the metal center. And then in a second process, we need back bonding, where this metal dxy or dxz or dyz orbitals are back bonding into the sigma star, the empty sigma star orbitals of dihydrogen. So we need an electron-rich metal center, D6, D7, D8, D9, so that we can have the back bonding. So that's electron-rich metals, because the sigma star of the hydrogen is populated, and the orbitals that are involved are typically the x square minus y square that is binding the dihydrogen. So in D8, this is for D8 metals, it must be the x square minus y square. It cannot be the dz square, because the dz square is filled. In a square planar complex, we have the we have an orbital that's square planar. That's the classic configuration. And so if we have 8 electrons, we have those 4 filled. So the accepting orbital at the metal for making the sigma complex here, there in the middle, can only be this one. That's the only one that can accept. So that's interacting with the filled orbital, sigma orbital of the dihydrogen. And the back bonding has to be between the axes, so it has to be either this one or that one, because now we defined that the hydrogen is binding within the square plane. It cannot bind in the apical position, because that's the Z square. The Z square is filled, no bonding. Yeah. In these 6 octahedral complexes, this is different, because they degenerate, both are empty. Because it is, because it's the hydrogen is, both hydrogens are activated. So the dihydrogen is formally homolytically cleaved in the inner coordination sphere. Both hydrogens are in the inner sphere. That's probably a sign. Well, I quickly go through the other two mechanisms, then we break up for a moment. We'll make it short. It bells me out. So here's the outer sphere mechanism, where now, so here in the inner sphere mechanism, so here in the inner sphere mechanism, the olefin can coordinate to the metal migratory in certain form. So the olefin coordinates to the metal center here then as the next step. In the outer sphere mechanism, the olefin does not coordinate. And typically, in order to have this happening, we need a heterolytic cleavage of the dihydrogen, which can work either in the presence of a basic ligand, so where the metal is Lewis acidic, the ligand is basic. So we have a polarization, delta plus, delta minus. This polarizes the dihydrogen bond, and we get basically a proton bound to the ligand and a hydride bound to the metal. So if you're an organic chemist, you'll love curly arrows. So in an oxidative addition, this would be an organic chemist's view. That's the homolytic leading to a dihydride. So that's heterolytic, leading to a monohydride. Where both electrons of the dihydrogen formally go into the metal hydrogen bond, and the lone pair at the ligand is capturing the proton. So here this is the polarity that is induced by the ligand metal setup, while here we have a homolytic cleavage, and formally both hydrogens have the same property, the same origin, the same reactivity. So in order for this reaction to go, we need either a ligand that is basic, so that can donate electrons. Amides are classic ligands. Oxides, carboxylates are all ligands that can do this. They have principally a lone pair still on the oxygen or the nitrogen that can act as a base. Or then we can have an external base. This is a bit more tricky, and it works in a stepwise manner, so not as concerted as I've drawn here, because 3 compounds don't meet in a solution. It's always 2 that meet. So here we may have the sigma complex, and then in the sigma complex, the hydrogen becomes more acidic, so the base attacks. So then we have a stripping off, and we get actually the monohydride, but the base is reversibly protonated and can put it back later. It's the same monohydride mechanism. So here is Noyori's catalyst, which is probably the prime example for direct hydrogenation via an outer sphere mechanism, but really any ligand that has a chelating carboxylate or an alkoxide can do exactly the same process. And then the last process that is maybe least relevant is the so-called hydrogenolysis, where the hydrogen is cleaved because we have a very basic ligand, but the ligand absorbs the hydrogen. So this could be a methyl group, for example. So we actually cleave again heterolytically, but now, if you like, this base is irreversibly protonated. So this departs. So then we get olefin coordination, microtree insertion, and now this is the base. So this can now be, this is now our new X here, and we get another hydrogenation. So then we're in a catalytic cycle. But so here again, one is a proton and one is a hydride, but one cleaves straight the product off. That seems to be stabilized by one electron processes, so it could be a classic feature for first row transition metals rather than the late ones. So the majority of the late transition metals, of the platinum group metals, would work either via an outer sphere or inner sphere, homolytic, heterolytic dihydrogen transfer. Good. We break. We'll make a break and then we talk a bit. What do we do? We meet in, how long do you need a break?